Thank you very much for the introduction. Yes, as already introduced, I will be talking about combining buffered I/O and direct I/O in distributed file system. Unfortunately, Yingjin Qian was unable to come here today, so I will present on his behalf. So first, in the last talk, we quickly had a small way for buffered I/O and direct I/O, and of course for Linux we have the default mode that is buffered I/O, which is utilizing, of course, the Linux page cache. And for over 20 years now, we have also an alternative I/O mode, which is called direct I/O, and it bypasses the Linux page cache, and it can be more beneficial in certain situations. For instance, you could avoid double buffer situation when you already have a database that is doing the caching for you, or you don't need the cached pages. So, but how much beneficial can it be? And so what you see here is basically the local LDistFS performance over various I/O sizes that you see on the x-axis. And basically the red tones are here for write and the blue ones for read. And what you see here for buffered I/O is that basically the performance stays relatively the same, right? Regardless if you have 4K or 256 I/O exercises. For direct I/O, we start slower, but then at around 1 megabyte, we're already significantly faster than buffered I/O. So why isn't it more used? Because it is still, usually buffered I/O is still mostly used. And there are various challenges that hinder the wide adoption from direct I/O. So first of all, of course, users tend to use the more familiar I/O mode, which is buffered I/O. And also there are some alignment constraints that can be difficult to accommodate, right? So your offset size and memory buffer address must be aligned, and this is typically to the sector size. You can already get this information nowadays with these .x system calls that you can then use. But oftentimes, if you are using an application, you cannot just rewrite the whole I/O layer to accommodate for direct I/O. So it remains often unused, and it's also unclear when it performs really better. We see here for the I/O request size, after 1 megabyte, it can become better. So we propose here that we can combine the benefits of both, so the performance of both, transparently within the file system and make this decision instead of the user. So transparent in that sense. The decision is not only based in our work on the I/O size, but we also take additional variables into account, like the log contention. We'll see what that means later. And then also additional optimizations like the server-side write-back and others. We implemented this in the Lustre parallel file system. And before I start, I want to do a little bit of a background, specifically of the cost of the page cache. And so what you see here is basically the specific case of a 16 megabyte I/O size, and then we look with perf where the time is actually going. And only about 20% of the time is really going to copying the data from user space to the page cache. More than 40% is page cache management. And so page cache management includes page allocation, also locking in the page cache, LIU management for aging and reclaiming, and so on and so forth. There's also others. So for instance, BGFS sets some pages to dirty, right? And overall, if you don't need this overhead, and you can use direct I/O, you are a lot faster. This is what you see here. So for ext4, the difference is a little bit starker than it is in the network file system, because of course, BGFS and Lustre there's also the network communication involved. But you see overall the trend where direct I/O is better. So next is, for those unfamiliar with how Lustre, the architecture really looks like, some basic terminology here, and basically what you really need to know is that there are 3 major components. The first one is the Lustre client. This is, of course, how the user interacts with the file system via the mount point. And then you have also parts that deal with the metadata. That is what we call the metadata servers and metadata targets, or short MDT. And then you have the OST, the object storage target, where the data is actually stored. And there's also some metadata parts like file sizes stored. So then the next part, Lustre, of course, as one of the strongly consistent file system, behaves as any other local file system. And so it uses a distributed log manager that It's basically used for file synchronization, metadata access. And what is important here that these specific components that you've seen, like the OST or an MDT, they all have their own distributed lock namespace. And clients can get a copy of that lock locally in a shadow namespace. And basically what that means is if one process on one node is accessing a file, it gets the lock for as much as can possibly can. And then if a second node wants to write also in a conflicting offset, this lock needs to be revoked. And if you do that repeatedly, you get basically lock ping pong, or what we call it lock thrashing, and this then degrades performance. So to now look into where buffered I/O and direct I/O are better. So both have their pros and cons, and buffered I/O really is better performance-wise when you deal with small I/O sizes that we've already seen on the first slide. And it's also great for hiding the latency of high latency storage like magnetic disks. Also for unaligned I/O it's great because the page cache basically takes care for you that it's aligned, and for direct I/O you need to do that yourself in user space. So on the other hand, direct I/O becomes better when you have large sequential I/O. Again, we have seen this on the first slide. And also for if you have many running processes, it actually doesn't scale that well, and also for many nodes. And of course, if you don't have a lot of memory available for the page cache, then also direct I/O makes more sense. So in our work, the areas of improvement are that we want to have the best of both worlds, basically, as good as we can. And also, while we're at it, remain the direct I/O alignment constraints and make that also automatic in the file system. And then some additional improvements for many small files and for file fragmentation. Now, the features here you see on the right, and there are also the abbreviations which we're using in the remainder of the talk. And original Lustre I will call vanilla. And we'll start with the first two, which is unaligned direct I/O support and client-side I/O mode decision. So basically for the unaligned direct I/O mode support, basically the Lustre client is doing that alignment for you, and if it's not perfectly aligned, then it of course needs to ask the storage server to read the data to accommodate for that alignment, and then after it's read from the servers, you can then write in an aligned way. Of course, there's an overhead attached to this. But in general, what we've seen is that it's still better for large exercises than using buffered I/O. Now for the client-side I/O mode decision, which we call auto I/O. So the primary I/O mode decision in this algorithm is revolving about the I/O size. And this is because it's the most important and the largest contributor to performance. And you see this down here. So this is, in this case now, a Lustre file system, and you see the test bed later. But in this case, what we can do is we not only have one threshold when we decide when to switch from buffered I/O to direct I/O, we actually have two. And the idea here is that there's a range for which buffered I/O always performs better, and there's a range where direct I/O always performs better. But in between, there's kind of a decision window where it's not quite clear when something is better. And in that sense, you can change the small I/O and the large I/O thresholds to basically force buffered and direct I/O, and this is why you see here direct I/O and buffered I/O over the complete scale. So in this decision window here, we test also for lock contention, and the assumption here is if you have a lot of lock contention, then it basically when direct I/O becomes more beneficial, it shifts to the left. So this is this large threshold here. And the same is for memory pressure and also lower cache usage. So in our initial experiments, we set this default decision window from 32 kilobytes to 2 megabytes, like you see here. So I want to show now a little bit more of the preliminary analysis here. So what does that actually mean when we have lock contention? And in this case, we created a lock contention workload. This is not in the paper, so this is specifically for this talk, in which you can see that under extreme lock contention, so before we had kind of the 2 megabyte where it was on par. Now under lock contention, direct I/O becomes more beneficial the smaller the exercises become. And even for 256K, it's kind of close. We see, so this is an extreme log contention case, and also the smaller the I/O sizes get, the worse the log contention becomes. But this is one of the cases, and we will later see that even for 64K, direct I/O can become more beneficial. The same thing we can also do with cache over usage, and that means one of the things that we test in our algorithm is whether you will reuse things that you actually put in the page cache. And if you don't do that, well, then pages get evicted, and then direct I/O also becomes more usable. And in this case, we are on par already for buffered and direct I/O here on the 256K case. So again, also on the memory constriction and log contention, direct I/O can become beneficial earlier. Okay, so the next parts are the other optimization that are going on top of that. The first one is the server-side write-back. So by default and in vanilla Lustre, we are using write-through on the servers. What we've added here is that we can also use write-back on the servers up to a threshold. So by default, we say, okay, this is what we've seen in the first slide, which is can be used as a backend storage for Lustre, LDXFS, that under 64K, it's more beneficial to use buffered I/O instead of direct I/O. And this is accommodating that. The next part is cross-file batching for buffered writes, and this we're calling cross-batching. Normally for vanilla Lustre, it batches the dirty pages into one large bulk RPC to improve network and disk efficiency, right? You don't want to send around small RPCs all the time for I/O operations. But if you don't fill these bulk RPCs up, then you can prolong these flush operations, especially if you're having many, many small files that are under 1 megabyte big. So what this cross-batching does is basically just batching dirty pages of several files. Then finally, we have delayed allocation. This is something what many file systems have already supporting, and this further improves the write-back mode of the server-side write-back, and is used to reduce file fragmentation. And this use case is specifically for strided I/O that going to single shared files. And basically what happens here is, of course, that the blocks are allocated later on the server, and so we can collect and merge smaller and non-contiguous requests, and then instead write down a larger piece of the file. Now, I want to quickly also talk about consistency. Of course, there are some potential for consistency conflict that could hurt the strong consistency guarantees. For example, one node is currently using buffered I/O and has something in the page cache that isn't flushed yet, and another node would use direct I/O to write into exactly the same region. So in that case, these specific regions could overlap, but because we have a distributed log manager, this protects against such conflicts. And this also is the same for unaligned direct I/O. And overall, it has no impact regarding the strong consistency guarantees that Lustre has. Regarding usage, all features and most of the individual thresholds you can control via Lustre LCTL. So for instance, if you want to enable auto I/O on the client, you can use this command, and you can also toggle the individual checks and thresholds within the I/O algorithm. The next part is, of course, for the server, you can do the same thing for server-side write-back. The default, like I said, is 64 kilobyte, but you could change that also. And the same for all the other improvements that I just shown. We have our artifact available, of course, so you can check it, and there you will find all the settings that you can use. So now to the evaluation. We are using 3 file systems here. One is Lustre, and of course the configuration is similar to all file systems, but the servers have a NVMe storage backend. We're using up to 32 client nodes, and we chose specifically these 2 other file systems because BGFS has 2 interesting file cache modes. So by default, the buffered mode, this is this one, is using write-back and read-ahead off by using static buffers. But there's also another mode which relies on Linux kernel mechanisms, and it can actually also switch to direct I/O, but only on one specific threshold. But in that sense, it is directly comparable to auto I/O if it had only a single threshold. For OrangeFS, this specific version of OrangeFS does not integrate with the page cache, so everything on the client is synchronous, but it offers 2 server-side modes. First is the alt AIO, which is buffered asynchronous I/O. So write-back basically, and the other one is direct I/O, which is write-through, which vanilla Lustre is using. So please refer to the to further experiments to the paper because we don't have time to go over all of them. But yeah. So the first and most important use case that we have is single process I/O streaming. And basically what we can see, we have the write on the left and the read on the right. That basically auto I/O can follow whatever is the best setting, right? So auto I/O in the beginning uses buffered I/O because the I/O sizes are small. There's no lock contention here, it's just a single process. And then after direct I/O gets better, and this is kind of the same here for read too, right? So this is the first, of course, sanity check, but this is how auto I/O works. To go to much more difficult use cases here, we have the IO 510 node challenge, and this is specifically the MD test hard test, which generates many small files, and the small files are actually so small and they're in a single directory that auto I/O does not, the auto I/O algorithm always uses buffered because it is not in this decision window, it's below the small threshold. We also have two Lustre cases here. One is on 1 mount point and one is on 4 mount point. And what Lustre can do is that you can have multiple mount points and assign specific processes to those because there also are some VFS locking bottlenecks that we would see here. And this is actually the case here. So we have the vanilla case, server-side write-back and cross-batching, but the performance is kind of the same because it's bottlenecked here by the VFS. If we're using 4 mount points, then you see here, okay, we have improvements here. And for delayed allocation, this has no impact because we're only on a single directory. Okay, for read, we also have significant improvements here concerning the other file systems. But because we are reading here, there's not this same VFS lock contention, and therefore they are more closely together than 1 mount point and the 4 mount points. So the next one is IOR hard. This is also from the 10 node challenge, and what it does is it generates unaligned strided IO. And this specific IO size is in this decision window because remember we started in the small threshold at 32 kilobytes, and it goes to a single shared file. And also, quick mention, both BGFS and OrangeFS don't support unaligned IO, and they are fallback to buffered IO in this case. But what I also want to highlight here, for Lustre buffered I/O vanilla, server-side locking, so actually I did not say that earlier, but one of the things that Direct.io can do in Lustre is that it can take the locks on the client's behalf, so there's less lock thrashing here. And for the buffered I/O, we actually have 3.5 million lock callbacks here that are disappearing for Direct.io. And here for efficient allocation and server-side write-back, we have the best performance. For read, we don't have the same lock contention, so auto I/O stays in buffered I/O mode. So lastly, I want to talk about a real-world application. This is NEC 5000. This is from the computational fluid dynamics application, a very classic HPC workload as a bulk synchronous application. We are running 512 processes. Each are writing in one 600 megabyte file. Per job step, so it's alternating computation and then I/O phases. A 10-minute workload generates over around 600 gigabytes of data overall. And what's interesting here that we have a wide I/O size distribution, right? We have very small files that are under the small threshold. We have large that are over the large threshold, and we have decision window files in the middle. What does the performance look like here? Again, for this case, where we don't see improvement is for cross-batching because it's, again, only a single file at a time, right? So it's not multiple files, so it doesn't help here, and also delayed allocation doesn't help much. But we see that the performance for auto I/O and server-side write-back gradually improves. And some of the things that you can also do is that you can look at the I/O statistics, and one of the things that you will see as well, there's a lot of lock contention because we're writing to a single shared file. And so over 130,000 I/O requests that would otherwise fall into default buffered mode were chosen to use direct I/O. And it helps quite a bit. Okay, to conclude, so we have presented the transparent approach to combine buffered I/O and direct I/O within the file system. We keep the strong consistency guarantees, and the key technologies here, of course, we have client-side improvements for auto I/O and this algorithm, but we also have server-side improvements for server-side write-back Regarding productization, so DDN and Whamcloud has already been working on it, and the unaligned direct I/O support has already been merged in Lustre 2.16. This is strictly opt-in, and you must use for open the ODirect flag as well. Hybrid I/O, and this is the basic auto I/O case that is depending on the I/O sizes to change, is planned for Lustre 2.16 and beyond, and then it will gradually improve the optimization that we've seen. In our artifacts, you will have all the links to the issue tracking, so you can in the future also check if these specific features have been merged into Lustre mainline. So for future work, we want to conduct an extensive performance analysis, because what we've seen in our tests, although our current thresholds work well, there's a much more that we can learn here. So it doesn't only depend on I/O sizes and thresholds. There are also hardware configurations, cluster configuration, and specifically also application workloads. One application might be more lock contention than another one, and then actually when direct I/O becomes beneficial changes again. So, and the idea is once we have that, we can have basically an automatic threshold adjustments during runtime as well. Finally, server-side algorithm currently only considers the I/O size, less than 64 kilobytes, and this should also consider the server state, like how much memory is available, and so on. And with that, I thank you.